Hello everyone, today we'll study elementary number theory. First of all, let me introduce divisibility. Let a and b be integers. If there exists integer c, such that ac equal to b, if there exists integer c such that a times c equal to b, then we say a divides b. Denoted by a divides b. So this is a vertical bar. A divides b. This is a vertical bar. This is a vertical bar. Now next, let me show you what does it means. Let me show you an example. For example, if 2 times 6 equal to 12, 2 times 6 equal to 12, here we see that 2 times the integer equal to 12. Then we can say, here we can say 2 divides 12. If a times the integer equal to b, we can say a divides b. If a times the integer equal to b, we can say a divides b. Here's 2 times the integer equal to 12, we can say 2 divides 12. Another example, 3 times 7 is 21. Since 3 times the integer equal to 21, we can say 3 divides 21. So keep this idea in mind. For divisibility, keep the following idea in mind. A divides b also means the following. This statement a divides b also means the following. First one, if a divides b, we can say a is a factor or divisor of b. If a divides b, we can say a is a factor or divisor of b. For example, 2 divides 12, we can say 2 is a factor of 12. If 2 divides 12, we can say 2 is a factor of 12, or 2 is a divisor of 12. 2 is a factor of 12, or 2 is a divisor of 12. 3 divides 21, we can say 3 is a divisor of 21, or 3 is a factor of 21. 2. We can say if a divides b, we can say b is a multiple of a. If a divides b, we can say b is a multiple of a. For example, 2 divides 12, we can say 12 is a multiple of 2. 3 divides 21, we can say 21 is a multiple of 3. 3. If a divides b, that means the operation if I take number b divided by a, the operation if I take b divided by a, it can be divided evenly. This operation b divided by a can be divided evenly. It can be divided evenly. For example, 2 divides 12. If I take 12 divided by 2, there's no remainder. If I take 12 divided by 2, I get exactly 6 with no remainder. 3 divided by 3 divides 21. If I take 21 divided by 3, there's no remainder. I get exactly 7, there's no remainder. So if A divides B, the operation B divided by A has no remainder. It can be divided evenly. Now let's look at some simple examples about divisibility. Divisibility is a statement. A divides B, that's a statement. It could be either true or false. A divides B, that's a statement. It could be either true or false. Determine the true value for each of the following statements. First one, 2 divides 6. Is it true or false? 2 divides 6. Now ask yourself, can we find 2 times some integer equal to 6? Can we make 2 times some integer equal to 6? If we can find some integer such that 2 times the integer equal to 6, then this statement 2 divides 6 is true. So here we know that 2 times 3 is 6. 2 times 3 is 6. So 2 divides 6. So this is a true statement. This is a true statement. Next example. 4 divides 23. Is it true or false? Ask yourself, can we find integer here such that 4 times the integer equal to 23? If we can find integer here to make 4 times the integer equal to 23, then this is a true statement. Otherwise, this is a false statement. We know that 23 divided by 4 is not a whole number. 23 divided by 4 is not a whole number. So there does not exist any integers here to make 4 times the integer equal to 23. So this is a false statement. We cannot find such integer here because 23 divided by 4 is not a whole number. So this is a false statement. Next. 5 divides 75. Is this a true statement? Is this a true statement? Ask yourself, can we find integer? Can we find integer here such that 5 times the integer equal to 75? Can we find integer here such that 5 times the integer equal to 75? We know that 75 divided by 5 is 15, which is a whole number. So here we can see that 5 times 15 is 75. Since I can find integer here such that 5 times 15 is 75, that means 5 divides 75. This is a true statement. Since 5 times the integer equal to 75, that means 5 divides 75. This is true. Next example. 7 divides 48. Is this a true statement? Is this a true statement? Ask yourself, can we find integer here such that 7 times the integer equal to 48? Can we find integer here such that 7 times the integer equal to 48? We know that 48 divided by 7 is not a whole number. 48 divided by 7 is not a whole number. So there does not exist any integer here such that 7 times the integer equal to 48. So this is a false statement. If a statement is false, we say 7 doesn't divide 48. If this is a false statement, we say 7 doesn't divide 48. For example 2. If 4 divides 23 is a false statement, we say 4 doesn't divide 23. Next. 6 divides 0. Is this true? Is this statement true? 6 divides 0. Is this a true statement? Ask yourself, can we find an integer such that 6 times the integer equal to 0? Can we find an integer here such that 6 times the integer equal to 0? We know that 6 times 0 is 0. 6 times 0 is 0. Since 6 times the integer equal to 0, that means 6 divides 0. Since 6 times the integer equal to 0, that means 6 divides 0. So this is a true statement. Next, how about 0 divides A? Is Is this a true statement? 0 divides a. Is this a true statement? Ask yourself, can we find an integer such that 0 times the integer equal to a? Can we find an integer here such that 0 times the integer equal to a? That's impossible. 0 times every number is 0. It won't be a. That's impossible. We cannot find any integer here because 0 times any integer. 0 times any integer is 0. It won't be a. This can never be true. 0 times any integer is always 0. It won't be a. So since we can never make this true, 0 doesn't divide a. Since we cannot find any integer here to make 0 times the integer equal to a, this statement is false. If this statement is false, we say 0 doesn't divide a. If this statement is false, we say 0 doesn't divide a. Next, let a be a real number. Let a be a real number. A divides 0. Is this true? Is this statement true? Let a be a real number. Is the statement a divides 0 true? Let a be a real number. Is the statement a divides 0 true? So ask yourself, can we find some integer here such that a times the integer equal to 0? Can we find integer here such that a times the integer equal to 0? If we can find integer here such that a times the integer equal to 0, then this is true statement. If we cannot find any integer here to make a times the integer equal to 0, then this is a false statement. Here we can see that a times 0 is 0, no matter what a is. A times 0 is 0, so this is a true statement. Since a times the integer 0, negative 0. Since a times the integer is 0, that means a divides 0. Since a times the integer equal to 0, that means a divides 0. Next, let b be a real number, and b is not 0. Let b be a real number, and b is not 0. Is the statement 0 divides b true? Let b be a real number, and b is not 0. Is the statement 0 divides b true? So ask yourself, can we find some integer such that 0 times the integer equal to b? Can we find integer here such that 0 times the integer equal to b? We know that 0 times every number is 0, but b is not 0. So no matter how you multiply, it cannot be 0, it cannot be b. 0 times every number is 0, but since b is not 0, no matter what we put here, 0 times this number, it won't be b. So this is a false statement. This is a false statement. Number 7 is a true statement. This is false statement. So 0 doesn't divide b. If this is a false statement, that means 0 doesn't divide b. So keep this idea in mind. Note. For any integer, for any real number a, for any real number a, we always have a divides 0. For any real number a, we always have a divides 0. That's one property about zeros. For any real number a, we always have a divides 0. So every number divides 0. That's one property about 0. Every number divides 0. For any real number a, we always have a divides 0. That means every real number divides 0. Every number divides 0. Next. For any non-zero real number b, for any non-zero real number b, for any non-zero real number b, we always have 0 doesn't divide b. For any non-zero real number b, we always have 0 doesn't divide b. So 0 doesn't divide any non-zero numbers. Every number divides 0, but 0 doesn't divide any non-zero real numbers. That's two special cases for 0. Every number divides 0, and 0 doesn't divide any non-zero real numbers. Those are two properties about 0. Keep in mind. Next, let me ask you one thing. Do you know the difference between these two symbols? What's the difference between this symbol and this symbol? This symbol is called divides. For example, A divides B, 2 divides 12. This symbol is called divides. What does this symbol mean? This symbol means something is divided by. This symbol means something is divided by something. For example, 20 is divided by 10. 30 is divided by 3. This symbol means divided by. This symbol means divides. So note, these two symbols are different. These two symbols are different. These two symbols are different. This symbol is called divides. For example, A divides B, 2 divides 12. This symbol is called something is divided by something else. Divided. This symbol is called divided by. For example, 10 is divided by 2. 20 is divided by 5, for example. So they are not the same. A divides B. This is a statement. If I say A divides B, this is a statement. A statement may be true or false. A statement may be true or false. A statement could be true or false. This is statement. A statement could be either true or false. If I say A is divided by B, what does this mean? This is operation. A is divided by B. This is operation. If it's operation, the result of operation is a real number. If this is operation, A is divided by B, the result is a real number. For example, 3 divides 12. This is a statement. It could be either true or false. Since 3 times 4 is 12, this is a true statement. Since 3 times the integer 4 equal to 12, this is a true statement. And how about this symbol? 3 is divided by 12. What does this mean? This represents a number. This represents a number. 3 divided by 12. This is a real number. This number could be reduced as 1 over 4. Three is divided by 12. This is a real number. It could be reduced as a fraction, as a real number 1 over 4. So this is a statement. 3 divided 12, a vertical bar is a statement. It could be either true or false. And we know this is a true statement because 3 times 4 is 12. This is a true statement. And the other symbol, 3 with a slash here, this symbol means divided by. When 3 is divided by 12, this represents a real number. It could be reduced as 1 over 4. So be very, very careful about these two operations, these two symbols. This means something is divides, something divides something else. This symbol means something is divided by something else. There are two different symbols. Be very, very careful. This is a vertical bar. This is a slash. They are not the same thing. They are not the same thing. A divides B is a statement. It could be either true or false. A is divided by B. That's a real number. That's an operation. It represents a real number. Next example, show that 20 divides 41 to the power n minus 1 for all integer n greater than or equal to 0. How can we prove it? If we try to prove it directly, try to show 20 times something equal to 41 to the power n minus 1, it may be too hard. Another approach is we can try to prove this by mathematical induction. Proof by induction. We first of all verify that this statement is true for the first n. That's the basic step. Verify that this statement is true for the first n. First n is 0. Here n is greater or equal to 0. First n is n equal to 0. First of all, verify that this statement is true for the first n. So when n is 0, 41 to the power n minus 1 equal to 41 to the power 0 minus 1, which is 1 minus 1. 1 minus 1 is 0. 20 divides 0. Is this true? We know that every number divides 0. For any real number, we have this number. Every number divides 0. For any real number a divides 0. So 20 divides 0. This is always true. Every real number divides 0. Every real number divides 0. This is true. So 20 divides 0. This is true. Every real number divides 0. So the statement 20 divides 41 to the power n minus 1. This is true when n is 0. When n is 0, this number is 0, and 20 divides 0 is true. So this statement is true when n is 0. That's the basis step. Next, the inductive step. For the inductive step, assume this statement is true for k. Assume this statement is true for k. Assume 20 divides 41 to the power k minus 1. Assume this statement is true for k. We try to prove that this statement is also true when n equal to k plus 1. Now, assume 20 divides 41 to the power k minus 1. Then what does it mean? If 20 divides this number, that means there exists a real number. That means there exists a real number m, such that 20 times m equal to 41 to the power k minus 1. If 20 divides this number, that means there exists an integer here, such that 20 times m equal to 41 to the power k minus 1. If 20 divides this number, means there exists an integer here, such that 20 times the integer equal to 41 to the power k minus 1, where m is an integer. So if a divides b, that means a times the integer c equal to b. That's what it says here. 20 divides this number, 41 to the power k minus 1. That means 20 times the integer equal to 41 to the power k minus 1. Same as a divides by a divides b. A divides b means a times the integer equal to b. So treat this as a, this as b. This is a, this is b. And treat this as c. 20 divides 41 to the power k minus 1 means 20 times the integer equal to 41 to the power k minus 1. Then if I simplify this expression, I can write 41 to the power k. I can isolate 41 to the power k. 41 to the power k equal to 20m plus 1. If I try to isolate 41 to the power k, I can bring 1 over. So 41 to the power k equal to 20m plus 1. We can use this as the induction hypothesis. Now, when n equal to k plus 1, we try to prove this statement is true when n is k plus 1. So we try to prove 20 divides 41 to the power k plus 1 minus 1. We try to prove that 20 divides 41 to the power of k plus 1 minus 1. So let me simplify this expression first, and then try to show this number is divisible by 20. Let me simplify this number first. Here, 41 to the power of k plus 1 minus 1. It can be rewritten as 41 to the power k times 41 to the power 1 minus 1. 41 to the power of k plus 1 can be rewritten as 41 to the power k times 41 to the power 1 minus 1 stays the same. Then by induction hypothesis, by induction hypothesis, 41 to the power k is 20m plus 1. By induction hypothesis, 41 to the power k is 20m plus 1. So we have 20m plus 1 times 41 minus 1. So here, 41 to the power k, by induction hypothesis, that's 20m plus 1 times 41 minus 1. If I distribute 41, I have 41 times 20m plus 41 minus 1. If I distribute 41, I have 41 times 20m plus 41 minus 1. So 41 times 20m plus 41 minus 1 is 40. 41 minus 1 is 40. 41 times 20 is 820. 41 times 20 is 820. And 41 minus 1 is 40. We try to show 20 divides this number. So I can try to factor 20 out. If I factor 20 out, 820 divided by 20 is 41m. 820m divided by 20 is 41m. 40 divided by 20 is 2. Since m is an integer, 41 times m plus 2 is also integer. Since m is an integer, then 41 times m plus 2 is also integer. Since Since 41 to the power of k plus 1 minus 1 equal to 20 times 41m plus 2, where 41m plus 2 is an integer. Since this number equal to 20 times 41m plus 2, and this is an integer, then 20 divides 41 to the power k plus 1 minus 1. Since this number equal to 20 times the integer, then 20 divides this number. Since this number equal to 20 times the integer, then 20 divides this number. So 20 divides 41 to the power of k plus 1 minus 1. If c equal to a times b, then we can say a divides c. If c equal to a times b, where b is an integer, then we can say a divides c. If c equal to a times b, that means b is an integer, that means a is a factor of c. If c equal to a times b, then a is a factor of c. So a divides c. Same thing here. This number equal to 20 times the integer. That means 20 is a factor of this number. That means 20 divides this number. Let's complete the inductive step. This statement is also true when n equal to k plus 1. This statement is also true when n equal to k plus 1. Let's complete the inductive step. Next example, show that 7 divides 9 to the power n minus 2 to the power n for all integer n greater than or equal to 0. For this problem, we can try to prove by induction. If we try to prove by induction, we first of all verify the basic step. Verify that this statement is true for the first n. The basic step. Verify that this statement is true for the first n. First n here is n equal to 0. Verify that this statement is true for the first n. So we have 9 to the power n minus 2 to the power n. When n is 0, 9 to the power n is 9 to the power 0. 2 to the power n is 2 to the power of 0. 9 to the power 0 is 1. 2 to the power 0 is also 1. 1 minus 1 is 0. And we know that every number divides 0. Every number divides 0. So 7 divides 9 to the power n minus 2 to the power n when n equal to 0. So 7 divides 9 to the power n minus 2 to the power n when n equal to 0. The basic step, this statement is true for the first n. This statement is true for the first n. That's the basic step. Next, for the inductive step, we assume this statement is true when n equal to k. So we assume 7 divides 9 to the power k minus 2 to the power k. Assume this statement is true when n equal to k. We try to prove that this statement is also true when n equal to k plus 1. So let me simplify this expression first. 7 divides 9 to the power k minus 2 to the power k. Then that means 7 times the integer equal to 9 to the power k minus 2 to the power k. If 7 divides this number, that means 7 times the integer equal to 9 to the power k minus 2 to the power k, where m is the integer. Then we have two terms here. The term that looks more complicated is 9 to the power k. The term that looks more complicated is 9 to the power k. So let me isolate 9 to the power k. 9 to the power k equal to 7m plus 2 to the power k. If there are two terms here, isolate the term that looks more complicated. If there are two terms here, isolate the term that looks more complicated. Here, 9 to the power k looks more complicated. So I can bring 2 to the power k over. I get 9 to the power k equal to 7m plus 2 to the power k. We can use this as induction hypothesis. Now, when n equal to k plus 1, we try to prove that 7 divides 9 to the power of k plus 1 minus 2 to the power of k plus 1. We try to prove this. 7 divides 9 to the power of k plus 1 minus 2 to the power of k plus 1. That's what we try to prove. So I can start from here. Try to show this number 7 divides this number. So start from here. 9 to the power of k plus 1 minus 2 to the power of k plus 1. 9 to the power of k plus 1 can be rewritten as 9 to the power of k times 9 to the power 1. 2 to the power of k plus 1 can be rewritten as 2 to the power of k times 2 to the power 1. Then if I substitute 9 to the power of k is this. 9 to the power of k is this. So by induction hypothesis, by using the induction hypothesis, 9 to the power of k is 7m plus 2 to the power of k times 9 minus 2 to the power of k times 2 to the power 1. 2 to the power 1 is 2. So I can write it as twice 2 to the power of k. 2 to the power of k times 2 to the power 1. 2 to the power 1 is 2. I can write it as twice 2 to the power of k. Then I can distribute 9. I have 63m plus 9 times 2 to the power of k. Distribute 9. I have 63m plus 9 times 2 to the power of k minus 2 times 2 to the power of k. If I combine like terms here, positive 9 plus negative 2 is 7. I get 63m plus 7 times 2 to the power of k. Since I try to show 7 divides this number, I can try to factor 7 out. If I factor 7 out, this number can be rewritten as 9m plus 2 to the power of k. If I factor 7 out, this number can be rewritten as 9m plus 2 to the power of k. m is an integer, k is an integer. So 9m plus 2k is also integer. Since m is integer, 2 is an integer. So 9m plus 2k, 9m plus 2 to the power of k is an integer. Then, since 9 to the power of k plus 1 minus 2 to the power of k plus 1 equal to 7 times 9m plus 2 to the power of k, where 9m plus 2 to the power of k is an integer, then 7 divides 9 to the power of k plus 1 minus 2 to the power of k plus 1. That completes the inductive step. That shows that this statement is true. When n equal to k plus 1. So let's complete the proof by induction. Next, let me show you a theorem about divisibility. Let a, b, and c be integers with a not equal to 0. Let a, b, and c be integers with a not equal to 0. We have the following statements. First one, if a divides b and a divides c, then a divides b plus c. If a divides b and a divides c, then a divides b plus c. If a divides two numbers, then a divides their sum. If a divides two numbers b and c, then a divides their sum. Second statement, if a divides b, then a divides bc. If a divides b, second statement says if a divides b, then a divides any multiple of b. If a divides b, then a divides any multiple of b. B times c is a multiple of b. So second statement says if a divides b, then A divides any multiple of B. The third statement, if A divides B and B divides C, then A divides C. If A divides B and B divides C, then A divides C. This is called transitive property. If A divides B, B divides C, then A divides C. We can also consider this as, if A is a vector of B, if A is a vector of B and B is a vector of C, then A is a vector of C directly. If A is a vector of B and B is a vector of C, then A is a vector of C. That's this theorem here. It contains 3 statements. Let's prove each statement individually. Let's prove from the first statement first. If A divides B, A divides C, show that A divides the sum of B plus C. So how do we prove it? Start from what's given here. If, since A divides B, then by definition, A times some number, A times some integer k, equal to B, where k is an integer. If A divides B, then A times the integer k equal to B, where k is an integer. Since A divides C by definition, then A times the integer L equal to C, where L is an integer. If A divides C, means A times the integer equal to C. If A divides B, means A times the integer equal to B. That's the definition of divisibility. Then I have 2 equations. If I add them up, what do we get? If I add them up, I have AK plus AL equal to B plus C. If I add them up, I have AK plus AL equal to B plus C. Then I can factor, on the left side I can factor A out. On the left side I can factor A out. If I pull out A, I get K plus L equal to B plus C. So A times K plus L equal to B plus C. Consider this is integer, this is integer, this is integer. Consider there are 3 integers here. Since K and L, they are both integers, K plus L must be integer. Consider this is an integer. That's another integer. That's another integer. Since A times the integer equal to B plus C, since A times an integer equal to B plus C, where K plus L is an integer, then A divides B plus C. Since A times the integer equal to B plus C, then A divides B plus C. That's a proof of the first statement. If A divides 2 integers, then A divides their sum. Proof for statement 2. Proof for statement 2. If A divides B, then A divides any multiple of B. If A divides B, then A divides BC. That means if A divides B, then A divides any multiple of B. So, prove it. Since A divides B, then that means A times the integer k equal to B, where k is the integer. Since A divides B, that means A times the integer k equal to B, where k is the integer. Then we try to show A divides BC. We try to show A divides BC. In this equation, I try to have BC here, so I can multiply both sides by C. In this equation, multiply both sides by C. So AKC equal to BC. If I multiply both sides by C, I have AKC equal to BC. If I multiply both sides of an equation by C, I have AKC equal to BC. And since K is an integer, C is an integer, KC is an integer. Since A is an integer, since K is an integer, C is an integer, so KC is an integer. So since A times KC equal to BC, where KC is an integer. Since A times KC equal to BC, where KC is an integer, then A divides BC, then A divides BC. That's the proof of statement 2. Now statement 3. Proof for statement 3. If A divides B and B divides C, then A divides C. So let me put a statement here. Statement 3 says, if A divides B and B divides C, then A divides C. That's statement 3. Let's prove it here. Since A divides B, then A times the integer K equal to B. Since A divides B, that means A times the integer K equal to B, where K is an integer. Since B divides C, since B divides C, then B times the integer L equal to C. Since B divides C, then B times the integer L equal to C, where L is an integer. Since B divides C, B times the integer L equal to C, whereas L is an integer. Now, we try to combine these two equations together. In the second equation, BL equal to C. First equation says AK equal to B. Second equation says BL equal to C. If I plug in B here, if I replace this B with AK, because B equal to AK, if I replace this B with AK, I have AKL equal to C. If I replace this B with AK, because A times K is B, if I replace this B with AK, I have AKL here. If I replace this B with AK, I have AKL equal to C. Then if I simplify, this can be rewritten as A times KL equal to C. This can be rewritten as A times KL equal to C. Since K is an integer, L is an integer, K times L is an integer. Since K is an integer, L is an integer, so K times L is an integer. So since A times KL equal to C, and where KL is an integer, since A times KL equal to C, where KL is an integer, then here, since A times the integer equal to C, I can say A divides C. That complete the proof of statement 3. That complete the proof of statement 3. Next, Let's look at corollary. Corollary means a short theorem. Let's look at corollary. Corollary means a short theorem. Let A, B, C be integers. Let A, B, and C be integers. With A not equal to 0. If A divides B and A divides C, then A divides MB then A divides MB plus NC for all integers M and N. Let A, B, C be integers with A not equal to 0. If A divides B and A divides C, then A divides MB plus NC for all integers M and N. This proof is very simple. A corollary is called short theorem. A corollary is a short theorem. This proof is very simple. Since A divides B by the previous theorem, statement number 2, by the previous theorem, statement number 2, if A divides a number, then A divides any multiple of the number. If A divides a number, then A divides any multiple of the number. Since A divides B, then A divides MB by the second statement of the previous theorem. If A divides B, then A divides MB. If A divides B, A divides any multiple of B. Since A divides C, then A divides NC by the second statement of the previous theorem. If A divides C, then A divides any multiple of C. Then, together, A divides what? By the previous theorem, the first statement. By the previous theorem, the first statement says, if A divides B, A divides C, then A divides their sum. So here, since A divides this number, A divides this number, then A divides their sum. A divides MB plus NC. If A divides MB, A divides NC, M must divide MB plus NC. So that's this corollary. This corollary says the above corollary says that if A divides B and A divides C, then A divides any linear combination of these two numbers B and C. Then A divides any linear combination of B and C. A divides any linear combination of course with integer coefficient. N and M must be integer. And A divides any linear combination with integer coefficients of B and C. That's what this corollary says. That's what this corollary says. If A divides B and A divides C, then A divides any linear combination of these two numbers B and C. If A divides B, A divides C, then A divides any linear combinations with integer coefficients of B and C. The coefficient must be integers. So that's what this corollary says. Next, let me show you the division algorithm. Division algorithm says for all integers A and D, with D greater than 0, there exists unique integers Q and R, where R is between 0 and D. R is greater than or equal to 0, but less than D. There exists unique integers Q and R, where R is between 0 and D, such that A equal to QD plus R. For all integers A and D with D greater than 0, there exist unique integers Q and R, where R is between 0 and D. R is greater than or equal to 0, but less than D, such that A equal to QD plus R. Now, how does this work? Let me show you an example. It will make more sense to you. In order to see how does this work, let me show you an example. It will make more sense to you. Let's look at an example here. For example, let A equal to 100. Let A be an integer, 100. And let D equal to 12. D must be greater than 0. So let A equal to 100, D equal to 12. How can we find Q and R? This algorithm says there exists unique Q and R. How do we find Q and R? Do division. Take 100 divided by 12. Take 100 divided by 12. 12 goes into 100. 12 goes into 100 8 times. 12 goes into 100 8 times. 8 times 12 is 96. Remainder is 4. So here we can see that 100 equal to A times 12 plus 4. 100 equal to A times 12 plus 4. 100 equal to, I can write 100 equal to A times 12 plus 4. So by matching the format here, we can see that 100 is A, number A is Q, 12 is D, and number 4 is R. By matching the formula, we can see that 100 is A, number A is Q, 12 is D, number 4 is R. So that's how we find Q and R based on the given A and D. And note, in a division algorithm, A is called the integer A is called a dividend. The integer A is called a dividend. Q is called, D is called a divisor. D is called the divisor. D is called divisor. Divisor must always be passive. D is called divisor. Divisor must always be passive. Dividend A could be negative, but divisor D must always be passive. Q is called the quotient. Q is called a quotient. And R is called a remainder. R is called a remainder. Remainder must always be less than a divisor. R is called a remainder. Remainder must always be less than a divisor. Remainder could be 0, but it must always be less than a divisor. Remainder must always be less than a divisor. It could be 0, but it must be strictly less than a divisor. Next, let me show you a few more examples about division algorithm. For each of the following pairs of A and D, for each of the following pairs of A and D, find Q and R. Find Q and R. The division algorithm says for every pair of A and D, we can always find unique Q and R. So, for each of the following pairs of A and D, find Q and R. First example, A equal to 35, D equal to 3. Find Q and R. A equal to 35, D equal to 3. Find Q and R. So use division, use long division. 35 divided by 3. Do long division. 3 goes into 3 one time. 3 goes into 5 two times. Sorry, one time. 3 goes into 5 one time. 1 times 3 is 3. Remainder is 2. So this is Q. This is R. This is Q. This is R. Make sure the remainder must be less than the divisor. The remainder must be less than divisor. So we can check. 35 equal to 11 times 3 plus 2. 35 equal to 11 times 3 plus 2. 35 equal to 11 times 3 plus 2. We can check the answer. 35 equal to 11 times 3 plus 2. Number 2. A is 128. B is 25. Sorry, D is 25. Find Q and R. A is 128. D is 25. Find Q and R. Use long division. Take 128 divide by 25. 25 goes to 128 5 times. 5 times 25 is 125. Remainder is 3. 25 goes to 128 5 times. 5 times 25 is 125. Remainder is 3. So this is Q. This is R. Make sure the remainder must be less than a divisor. Remainder must be less than a divisor. Check an answer. 128 equal to 5 times 25 plus 3. 128 equal to 5 times 25 plus 3. Now, look at something different. With A is negative 49, D is 6. A is negative 49, D is 6. What should we do? Remember, for division, we cannot divide negative numbers like this. For long division, it won't work for negative numbers. What can we do? Long division won't work for negative numbers. What can we do here? Now, if A is negative, use the formula A equal to dq plus R. If A is negative, use the formula A equal to dq plus R to find Q and R. When A is negative, use this formula to find Q and R. Let me show you how. First step, find Q. For Q, you first of all take negative 49 divided by 6. Take negative 49 divided by 6. Then take something called floor function. This symbol is called floor function. What does floor function means? Do division first, I'll show you what does floor function means. Do long division first, I'll show you what does floor function means. Take negative 49 divided by 6. We get negative A and 1 over 6. Take negative 49 divided by 6, we get negative A and 1 over 6. Now let me show you what does the floor function means. Floor function. So if x is integer, s is integer, then floor function of x stays the same. If s is integer, floor function of x stays the same. For example, floor function of 1 is 1. Floor function of 10 is 10. Floor function of negative 5 is negative 5. If s is a whole number, floor function of whole number stays the same. Next, if x is not a whole number, then the floor function of x equal to the nearest whole number nearest integer to the left of x in the number line. If s is not a whole number, if s is not integer, then the floor function of x is the nearest integer to the left of x in the number line. For example, how do we find floor function of 1.7? Draw number line first. 0, 1, 2, 3, 4. Negative 1, negative 2, negative 3, negative 4. 1.7 is here. This is 1.7. 1.7 is not integer, so use this rule. Floor function of x, floor function of 1.7 is the nearest integer to the left of x in the number line. The nearest integer to the left, is number 1. So floor function of 1.7 is 1. How about the floor function of 2.5? 2.5 is here. This is 2.5. 2.5 is not a whole number, it's not integer. So the floor function of 2.5 is the nearest integer to the left of x. Nearest whole number to the left of x. Nearest whole number to the left is 2. Nearest whole number to the left is 2. Nearest whole number to the left of 2.5 is 2. How about floor function of 3.1? What's floor function of 3.1? 3.1 is somewhere here. When we take floor function, 3.1 is not integer, so use this rule here. Floor function of 3.1 is the nearest integer to the left of x in the number line. floor function of 3.1 is the nearest integer to the left of x in the number line. Nearest whole number to the left is number 3. Nearest whole number to the left is number 3. How about floor function of negative 0.6? Floor function of negative 0.6. Negative 0.6 somewhere here. Negative 0.6 somewhere here. The nearest whole number to the left. The nearest whole number to the left is negative 1. The nearest whole number to the left is negative 1. How about negative 2.3? Negative 2.3. Negative 2.3 is somewhere between 2 and 3. Negative 2 and negative 3. Somewhere here. That's negative 2.3. The nearest whole number to the left. The nearest whole number to the left is negative 3. How about negative 3.9? How about a floor function of negative 3.9? How about a floor function of negative 3.9? Floor function of negative 3.9. Negative 3.9 somewhere here, between 4 and 3, 3 and 4. That's negative 3.9, somewhere here, between negative 3 and negative 4. Round to the nearest whole number to the left. The nearest whole number to the left is negative 4. The nearest whole number to the left is negative 4. So floor function of negative 3.9 is negative 4. That's the rule for floor functions. That's the rule for floor functions. Similarly, we also have a special function called ceiling function. Ceiling function is very similar as a floor function. We don't need it for now, but we'll use it later. Let me give you introduction for ceiling function. We don't need it now, but we may use it later. We'll use it for the later class. Ceiling function of x. The rule is very similar. The rule for ceiling function is very similar. If x is a whole number, it's an integer, then the ceiling function of x stays the same. If x is integer, then the ceiling function of x stays the same. So ceiling function of number 7 is number 7. Ceiling function of 101 is 101. Ceiling function of whole number stays the same. Ceiling function of negative 50 is negative 50. Ceiling function of a whole number stays the same. But if s is not a whole number, if s is not integer, then the ceiling function of x equal to the nearest whole number nearest integer to the right of x. Then the ceiling function of x is the nearest integer to the right of x in the number line. If s is not integer, the ceiling function of x is the nearest integer to the right of x in the number line. For example, how do we find ceiling function of, say, 1.4? Draw number line first. 0, 1, 2, 3, 4. Negative 1, negative 2, negative 3, negative 4. 1.4 somewhere here. It's 1.4. Since 1.4 is not integer, for ceiling function of 1.4, use this rule. Ceiling function of 1.4 is the nearest integer to the right of x in the number line. Nearest integer to the right is number 2. Nearest integer to the right is number 2. Ceiling function of 3.4, 3.2. Ceiling function of 3.2, 3.2 somewhere here. That's 3.2. If we take ceiling function for 3.2, 3.2 is not a whole number, so we round to the nearest integer, nearest whole number to the right. Nearest whole number to the right of x in the number line. In the number line, the nearest number to the right is number 4. Ceiling function of 2.9. Ceiling function of 2.9. 2.9 is here. The nearest whole number to the right is number 3. How about ceiling function of negative 1.1? How about ceiling function of negative 1.1? Negative 1.1 is here, somewhere between 1 and 2. Negative 1, negative 2. Negative 1.1 is here. If I take ceiling function, round to the nearest whole number to the right. Nearest whole number to the right is negative 1. How about ceiling function of negative 2.1? Negative 2.1 somewhere here. Between negative 2 and negative 3. Round to the nearest whole number to the right. That's negative 2. How about ceiling function of negative 3.8? How about a ceiling function of negative 3.8? Negative 3.8 somewhere here. Round to the nearest whole number to the right. Nearest whole number to the right is negative 3. Nearest whole number to the right is negative 3. That's how we define ceiling function and floor function. For floor function, for the whole numbers, it stays the same. But for integers, round to the nearest whole number to the left. For ceiling function, round to the nearest whole number to the right. Now let's go back to this problem here. In order to find q, we take floor function for a divided by d. In order to find q, I take floor function for a divided by d. A is negative 49, d is 6. So for floor function, in order to find q, I take floor function for a divided by d. A divided by d is negative 49 divided by 6. That's negative a and 1 over 6. How do we take floor function for this number? How do we take floor function for negative a and 1 over 6? In the number line, negative 9, negative a, negative 7, negative 10, and so on. Negative a and 1 over 6 somewhere here. This is negative a and 1 over 6. For floor function, round to the nearest whole number to the left. For floor function, round to the nearest whole number to the left, which is negative 9. For floor function of negative a and 1 over 6, round to the nearest whole number to the left, which is negative 9. That's how we find q. So for q, in order to find q, take a divided by d, then take floor function. First of all, take a divided by d, then take floor function. I get q is negative 9. Next, find r. How do we find r? In order to find r, use the formula a equal to d times q plus r. In order to find r, use the formula a equal to d times q plus r. Plug in. A is negative 49. D is 6. Q is negative 9 plus r. A is negative 49. D is 6. Q is negative 9. Plug in. Find r. Solve the equation for r. 6 times negative 9 is negative 54. Then add 54 to both sides. R equal to 5. Add 54 to both sides. R equal to 5. So for number 3, Q is negative 9. R is 5. R must always be less than D. Remainder R must always be less than D. Q could be any number, but R must always be less than D. R must be a whole number, but it must be less than D. R could be 0, but it must be less than D. Next example, a equal to 115, negative 115. D equal to 9. A equal to negative 115, D equal to 9. So we try to find Q and R. We try to find Q and R. Division algorithm says there exists unique Q and R. But here we try to find Q and R, the quotient and the remainder. So for Q, take floor function of A over D. For Q, take floor function of A over D. A is negative 115. D is 9. Then take negative 115 divided by 9. We cannot use long division for negative numbers. So for negative 115 over 9, we can divide the positive numbers. 115 divided by 9. So negative 115 over 9 can be written as negative 12 and 7 over 9. Negative 115 over 9 can be rewritten as negative 12 and 7 over 9. I put a negative sign in the front, then simplify this improper fraction. I bring negative sign to the front. Simplify this improper fraction, I get 12 and 7 over 9. Then round to the, for floor function, we round to the nearest whole number to the left. Round this number to the nearest whole number to the left. In the number line, that's negative 10, negative 11, negative 12, negative 13, negative 14. Negative 12 and 7 over 9, somewhere here. That's negative 12 and 7 over 9. Round to the nearest whole number to the left. Round to the nearest whole number to the left, that's negative 13. That's Q. Once we know Q, we can find R using the formula A equal to DQ plus R. Use this formula to find R. Once we know Q, use this formula to find R. A is negative 115. D is 9. Q is negative 13. We are looking for R. 9 times negative 13. I get 117. I get negative 117. Plus R. Then I can add 117 to both sides. R equal to 2. I can add 117 to both sides. R equal to 2. So here, Q is negative 13. R is 2. Make sure the remainder must be less than the divisor. R must always be less than D. Q could be any number. Q could be any whole number. But R must always be less than the divisor. R must always be less than D.